is Tiffany. I'm an industrial engineering major at the U of A, and I am the team lead.
My name is Leo Delgado, and I am biosystems engineering here at the U of A, and I am the biomedical lead.
Hi, my name is Katie Tai. I'm a material science and engineering major, and I'm the materials lead.
Hi, my name is Rory Nagberry. I'm a mechanical engineering major and the mechanical lead.
Hi, my name is Tana McLeod. I am a mechanical engineering major at the U of A, and I am the technical lead.
Hi, my name is Kayla Griffith. I'm a systems engineer, and I'm the team's procurement lead.
We are Team 25510.
Dental instruments designed to reduce hand fatigue.
Within the dental industry, the process of cleaning teeth involves repetitive movements that put significant stress and strain on the muscles within the hand. According to studies done via the ADA, nearly 1 in 3 dental professionals suffer from musculoskeletal disorder development, with carpal tunnel syndrome being the most common developed disorder. This phenomenon, on average, forces dental professionals to retire 5 years earlier than their peers, missing out on potential career benefits and taking years away from a career they love.
Studies have shown that poor tool design is a leading factor in the development of these disorders, as small diameters and heavy tool weights require greater pinching force and muscle activation to utilize traditional tools. This issue is a devastating silent killer within the dental community, and sadly, its effects are more prevalent than we realize. Dental professionals shouldn't have to worry about this issue affecting the longevity of their careers, and that's why we are striving to redesign tools to work towards mitigating this problem completely.
During our visit to Tucson Biological Dentistry, Dr. Krisman explained how the instruments she uses every day contribute to hand fatigue and thumb strain. She showed us how the instruments are typically held and used during procedures, pointing out the specific positions and motions that create discomfort over time. For example, the tight pinching grip required when using a scaler places significant stress on the thumb, which can lead to strain during long procedures.
After visiting with our sponsor at Tucson Biological Dentistry, we were able to derive our system requirements. The ones that had the greatest impact on our design were ensuring that our dental instruments could withstand high temperatures up to 134 degrees Celsius or roughly 237 degrees Fahrenheit. That way they can survive the sterilization process. The next was to have the design fit a wide variety of hand sizes because we want our dental instrument to work for everyone who utilizes it. The last and arguably most important requirement is to reduce the overall hand fatigue.
Our material selections for the dental instruments were chosen in accordance with ISO standards for stainless steels and polymers used in dental instruments. The stainless steel chosen for our end threads is M12, which is equivalent to American Iron and Steel Institute 440B stainless steel. The polymer selected for our handles is polyphenylene sulfone. These materials were chosen for their biocompatibility, their ability to withstand repeated sterilization cycles up to 134 degrees Celsius, and their relatively low density, which helps reduce instrument weight and minimize hand strain.
After identifying our requirements with respect to both the desires of our sponsor, Dr. Krisman, as well as with respect to ISO dental standards, trade studies were conducted based on appropriate tool materials and existing ergonomic tool designs, which would inspire the direction behind each of our designs. As the weeks went by, we worked within SOLIDWORKS to bring these designs to life and continuously polish them to meet the major requirements that we had set out for.
Our first MVPs were simple prototypes that let us test basic attachment, weight, and overall function. Those early tests showed us what wasn't working, which directly shaped MVP 2. In the second iteration, we redesigned the tools with better thickness, reduced weight, and stronger connection points to make them more ergonomic and user-friendly.
After countless revisions, we were able to construct the following designs. Via FEA analysis, we were able to conduct simulations of each of our tools within an autoclave setting for both a single cycle and for a year's worth of cycles. From this analysis, we determined that our tools are more than capable of withstanding autoclave conditions due to their immensely high factor of safety in the face of sterilization. Additionally, we were able to also create proper part drawings that made the manufacturing process smooth for us, as we made an emphasis on incorporating appropriate tolerances and dimensions that would allow for easy production on the manufacturing end. Following both the analysis and manufacturing process, we were able to construct the finalized models as you can see here, consisting of a PPSU handle and a 440B steel end thread for the tools that require them.
The dental mirror uses lightweight PPSU, a thicker handle for comfort, engraved grip for stability, and a threaded end for easy head replacement. The double-sided tool also uses the PPSU with thicker ends, non-slip engraving, and threaded holes so the user can swap out different tool heads as needed. The microbrush features varied diameters, a curved shape for easier grip and reduced strain, plus a collet tip for quick replacement of disposable heads.
By using a surface electromyography system, we were able to test and verify that our dental instruments met the requirements for reducing hand fatigue. The software allowed us to choose the muscle groups as well as provided us with amplitude reports and fatigue reports.
Wait! We have to finish the IRB approval first! Get out of here, Diego! We have to fill out the IRB, we have to go to the website starting to fill out the IRB.
Before we can test with human subjects, we first need to apply and receive IRB approval. As a team, we worked very hard to compile all the necessary documentation and required learning. As a team, we learned about ethical requirements when working with human patients and wrote up the following documents. IRB protocol for human research, where we detailed how patients will be recruited, and EMG testing procedures and risk. Consent forms for participants, as well as signatures from required department authorization. This process took months of waiting on IRB document change feedback, but we finally got approval for testing with dental professional participants at Tucson Biological Dentistry.
As you can see, we are able to do EMG testing not only within ourselves but at Tucson Biological Dentistry. We can see how a dental professional used our typodon model as a surrogate cheek to perform a dental cleaning with both old and new instruments, following all IRB procedures. And when we go about testing, this is what the actual process looks like.
With help from Dr. Zhongming Li, a professor and doctor of orthopedic surgery and biomedical engineering, we identified key muscle groups involved with everyday dental procedures. Using our SEMG, we were able to perform both fatigue and muscle activity analysis to identify whether our tools were effective in reducing fatigue. From our muscle activation analysis, we were able to observe significant reductions in mean muscle activity via our tools in comparison to that of traditional tools. The reductions varied across instruments, ranging from anywhere between 10 to 50% based on the subject. While more testing with more hygienists can be done to further solidify these results, these numbers are a positive indicator of our tool's effectiveness in not only reducing stress within the hand, but also fatigue as well.
One of the key lessons learned for me during this project was the importance of documentation and reaching out to other professionals for help, specifically when it came to the IRB approval.
From my lessons learned, I realized just how important it is to be resilient and perseverant. Going through that experience really showed me how much you can accomplish when you stay committed and you keep pushing forward.
The biggest lesson I learned was to always be ready to pivot.
My biggest takeaways from this project is to 3D print early, 3D print often, and don't be scared to change your designs, and have a really great lab partner.
My biggest takeaway from this experience is that a great team really does make all the difference. And when everyone puts their heads together, anything is possible.
One of the key things I've learned throughout this process is that although sometimes the plans seem they are set in stone, they are just outlines at the end of the day, so it's really important to give yourself a lot of room to work with.
Throughout this experience, our team has come together to not only develop our engineering skills and abilities, but to grow together as a team and work towards developing a product that can make a difference for our community in need.
Through good times and bad, we lean on each other and our community to accomplish our goals and create designs that we believe will have a lasting impact within the dental community. Ultimately, we not only learned a lot about engineering, but also a lot about each other, and we're more than thankful for this experience for giving us the chance to make an impact and close out this final chapter of our times here at the University of Arizona.